Okay, so we're going to give you some help on 2.2 here. We'll start with question number 10. It says, what's the acceleration due to gravity at an altitude of 2.0 times 10 to the 6th meters above the Earth's surface? So if you think about the Earth being right here, we're going to be up here a little bit higher, specifically 2 times 10 to the 6th, or 2 million. So meters above the surface of the Earth. That's a lot of meters. Stop doing that. Stop doing that. Okay, we'll leave it alone. Assume that's in meters. Okay, so we're that far above the Earth's surface, but we have to remember that when we're doing acceleration due to gravity, that's a big idea. We're not asking for the force of gravity. We're asking for the acceleration due to gravity that far off the surface of the Earth. And so when we're talking about that, we're talking about little g. Okay, because remember, there's the universal equation, Newton's universal gravitational law, which says big G, m1, m2, all over r squared. The problem with this is that we have to know the mass of the second person, or second object. We don't want to know that. We just want to know the acceleration. So if you can think of Fg being mass times gravity, one of these masses cancels. And so when we're just looking for little g, it's always big G times the mass of the planet that we're on, and we're going to use Earth, over the radius of orbit squared. Now, I use the term radius of orbit because it's not the radius of the Earth. It's the radius from the center of the Earth to the center of the other object. So because we're not sitting on the surface of the Earth, we have to change this just a little bit. Now, a couple pieces of information we should know or need to know that may or may not be given here in the notes. It's not, so we're going to have to pull out some information that I'm going to pull out of the textbook, and then we'll kind of go from there. I'm just making sure it's not listed somewhere else first. It doesn't seem to be, so let me grab my book, and we're going to put out a couple of numbers that we're going to want to kind of keep track of whenever we're doing this planetary stuff. We'll start talking about the Earth and its mass and radius, which are going to definitely matter in this problem. We want to have that useful information close at hand. So the mass of the Earth, okay, roughly speaking, is 5.98 times 10 to the 24th kilograms. Now we measure in kilograms when we're talking about mass. So this number is ready to go the way that it is. When we talk about the radius of the Earth, okay, we have to understand that the Earth's not a perfect sphere. So this is what we're going to call the average or the mean radius of the Earth. And generally we're going to say this is 6.38 E6 meters. Now in the text you might see it, if you look some other places, you'll probably see it in kilometers, which would be 6.38 E3 kilometers. The problem with that is that we do everything else in meters, so we really want this to be in meters. So that's the distance from the center of the Earth to the surface of the Earth. But we're an additional 2 million meters above that. Okay, and so we have to keep that in mind when we do this calculation. Little g, when we're that high above the Earth's surface, will be equal to big G, which is a constant 6.673 E negative 11, times the mass of the Earth, which is a constant 5.98 E24. Remember that E is the scientific notation from the calculator. All divided by, and this is one of the places we get into trouble. We really need to make sure we get this done right. So I'm going to have 6.38 E6 plus, we had a 2 E6, right? It was 2.0 E6 was the number that we were given. That has to be squared. If you don't get that squared, it's not coming out right. Now, when I talked about using scientific notation in the calculator, it really simplifies the amount of parentheses that I need. And so I'm only going to have to use the ones in the denominator because of the squaring and the addition. So other than that, I'm pretty well safe to not use parentheses. So I'm going to start with 6.673 second, and it's the comma, produces that little uppercase E, but it's a little smaller, negative 11. times 5.98 second E 24. Now I can hit enter here if I want, enter, and then I can just hit divided by. It's going to pull that answer down, divided by. Because of the addition here, I do have to use the parentheses. 6.38 E 6 plus 2 E 6. Close parentheses. Now that right there, before I do anything else, I need to square that parentheses. And when I do, I get a little g of 5.68 meters per second squared. Let's take a second. Let's look at our answer there. Where are we at? 5.68 meters per second squared, just like we said it would be. That's not quite half the gravitational pull that we feel on the surface. We really have to continue to go up pretty high to get gravity to not matter. It's an effective deal over great distances. If you think about it, the Earth revolves around the sun. We're pretty far away from the sun, and yet we still manage to be pulled in by its gravitational pull. So there's definitely something to be said for the impact of gravity. Let's go ahead and look at another problem. Let's look at question number 14. This question is a really interesting question. I wish there were more elevators in Kimberly where we could go and actually experience this, but I think for the most part you've experienced it if you've been on an elevator before or been in a car going over a bump in the road. You're going pretty fast. If not, go down to the hospital this weekend, get on the elevator with a bathroom scale and see how this works out. We've got a 50-kilogram woman riding on an elevator. All right, so there's my 50-kilogram woman. Let's talk about the forces that are acting on her. We know that gravity is acting on her. That's mg. And we know that Fn pushes back. Now, as you're going in the elevator, there's the ground of the elevator pushing up, and your weight, your gravity is pushing down. That's it. Those are all of the forces that act on you. However, as the elevator behaves differently, there's going to be some different things that happen. So the sum of the forces, remember, always equals ma. And that's the key idea. That if I were to do the sum of the forces in this case, I would have Fn minus mg, because mg is downward, and that would equal, sometimes it equals 0. When I'm standing on a flat surface and there's no movement, I have 0 here. But it's always a safe bet to write ma here, because the sum of the forces will equal the mass times acceleration. Well, if I start plugging these things in, first thing I need to understand is that Fn is what we call the person's apparent weight. So that is really what I'm after, is Fn. I know I'm going to subtract her mass times gravity. It says that her mass is 50 kilograms times 9.8. Now I'm not using a negative 9.8 here because this is being subtracted. So I'm implying the negative based on the arrows in the problem. Equals 50 times, now what is actually happening to her? She is accelerating with the elevator, okay, upward at 1.5. Now, we have to understand, upward was positive. So we're going to say that this is a positive 1.5. Okay? Now, we should be able to finish calculating and solve this. If we take the 50 times 9.8, we should get 490. I think I've got that right. So I'm going to add 490 to both sides. Grab my calculator. And we'll slide you over here. Come on. Come on. All right, there we go. We have 50 times 1.5, and we're going to add 490 to get 565. Now, what's important to understand is normally her actual weight would be 490. So she's just gained 75 newtons of weight based on the fact the elevator is zooming up. And if you think about that experience of the elevator rising, that first moment before you caught to a constant velocity, there is that moment of feeling heavy or sunken into the floor. All right, let's do one more, and then we'll be good for this assignment. Let's clear it, and we'll start again. Let's just minimize down. All right. On question number, I think we're going to go to 16. Just want to make sure we have an understanding of how to set these up and work with the information that we're given. We have a 5 kilogram block. It's resting on a frictionless plane inclined at 10 degrees. So that's at 10 degrees. We have our block. We're just going to call that our block. And we want to know what the acceleration is as it accelerates down the incline. Now they did tell us it's a 5 kilogram block. Maybe that'll matter, maybe it won't. So we'll just go ahead and write that the mass is 5 kilograms. All right, to finish this question, we really need to talk about the different forces that act on it. We know we have mg coming down. We have Fn coming out of this inclined plane. Without friction, there are no other forces, and so we just need to break these down. This would be mg cosine theta, which we know is always equal to Fn. And then over here in the downward direction, right there, is mg sine of theta. Now that is the only force in this diagram that doesn't get canceled out by something else. You have to remember that this guy right here, gravity, was broken into its two components, here and here. So it doesn't exist as its own vector. It's now those two. But we have to remember that this vector, downward, gets canceled out with that vector there. So when I say the sum of the forces, literally the only force left is the mg sine of theta, that component of gravity. Now that, we know, will equal ma, because the sum of the forces equals ma. So if we get rid of our masses, which we could have put the 5 in, but it doesn't actually matter, we know that 9.8 times the sine of our angle, which is 10 degrees, should equal our acceleration down the plane. So we're going to grab our calculator. Let's see if I can slide over. There we go. 9.8 sine of 10. Do check your calculator consistently for mode questions. We get 1.70. So the acceleration is 1.70 meters per second squared down the incline. And that's it, guys. A lot of the same kind of stuff. We're breaking them apart, looking at how do we combine different things or how do we deal with angles. Good luck, and I'll see you in class.